Hey everyone. So today I'm going to talk about shared memory. Um, I'm going to compile all the codes. I'm going to start by deleting everything. Now I'm going to compile every single code in that chapter. All good. So this is the first example, which is the check memory for a rectangle. So the main concepts here to understand, to be straight to the point. First, we set up the x and y's and a pad, which means the location that we want to store and in the shared memory. So this is just a function to print the data. And here in the kernel, this is just is gonna all work the same in terms of read rows and columns. But this is how it's gonna work. First, we're gonna call this shared memory. It's a static shared memory. So this is a tile. This is the memory itself. This is the target of which location. We have it 16 and we have it 32 here. So, and here we map it from thread index to global memory index. This is how we map it on how the indexes to the global memory. And then this is how we store that specific thing, this thread. We store it in this location in the tile, which is the memory. And then we wait for the thread to complete. Once it's done, we load it. We load it to that specific output to the specific thread this way. All right, so this is the most important things. Now we're gonna keep doing that in a section of triangle way, and we can see it's going the same way. It's declaring the shared memory, mapping it, store it, synchronize it, then load it. So here is going by column read, column two. Here is different because we have two columns. So here, for example, we have shared memory, mapping thread, convert into transpose coordinates, because this is how we convert it to specific coordinates. Then we do the same thing. We store the operation that specific threads. We synchronize, then we load it ultimately. And here we have a row read column. So this is a triangle, but they're gonna all work as the same concepts as sharing, mapping, storing, then loading. Okay. All right. So here then eventually here in the main function, we call that kernel, and we can now okay. So here we call the print that in a specific kernel. Now we can try see the output, and here we have the tile is showing here in which shared memory that is being used. That went successfully. So this is the same concept, but this is a rectangle. This is square, and as we can see, it's gonna be going the same flow, declaring the BD AMX, the BD M32. But if we can notice before, we had a 1632, right? Because it was a triangle, 3216. But this time, because it is square, we have it 3232. This is just a function to print data. And then again, here it goes the same. Declare a shared memory, the specific X and Y. We map it into a global memory. We have a shared memory operation. We synchronize. Then again, um, we load that operation. And that's because it's the square one is like before we read columns and rows accordingly to the specific coordinates. And as you can see, is going all in the same flow that we've seen before in the previous example. And then here in the kernel we call that again in here. So this is the we call those kernels in here, every single one, and with here like just as like as before, one by one, right? And we can as well test this one. and we have the result. All right. So now we have seen this example. We're gonna see the rest. We have this constant read only. So this is different. This is a constant memory, and this is we define every coefficient of that, right, with a specific hexadecimal way. That's the coefficient radius, and here we initialize the data, print the data, and here is this is where we create a dictionary, in where we store the coefficient, and then we check the memory to sample. Here is just a double check the size of the memory. Here this is how we create, trying to target every point, or maybe all the coordinates in the radius, by declaring the temporary memory. Then that at the end put it as an output is in here. Then here we check result. This is how we check results in here, and we go down in the same flow as before. We declare shared memory in that specific target that we want to target. We index it to global memory. We read data from global memory into shared memory, and we read the hello part to shared memory. This is just like a way if we can read the specific location in the memory here, synchronize it, apply the centil, and here it's a loop to do called an enroll to store the results in certain of a loop. We want to store everything in a loop, at the end have it as an output. And here we have a centicil one read only. We'll do the same thing, shared memory, mapping, indexing, read data from global memory to shared memory, and then here we read it as before, and we apply the sense cell in here. When we enroll, this is how we store it in the setting of a loop. We store the result, and here we call all the kernels on those functions and stuff. This is very important as well to talk about. So this is how we declare the memories, and this is how we allocate the memories in a host, and then transfer all that into CUDA, and then we call that function and copy to the device, set up a constant memory with this function here, launch configurations accordingly, and then launch the send cell, the function that we just spoke before, and then a copy result back to the host, apply CPU send cell, check results, then launch read only cache kernel. All right, so then here we free above hosts and the CUDA. We can run this one real quick. And here we see everything in there. So the next one right now is the constant send cell. So it's pretty much like before, right? We declare the constant memory, the coefficient, we initialize the data, we set up the coefficient. Here was the difference comes in, where we have a CPU send cell in one dimension. And then here, check result, as we've seen before. This is the enroll kind of storing. And here we have a shared memory, index to global memory, index to shared memory for sensor calculations. So here it's kind of a little different from before. Index, this is index to memory for sensor calculations. Read data from a global memory into shared memory here. And here use a read hello part to shared memory, synchronize and apply the send cell. Enroll, this is a way of storing it in the way of a loop. And here we index that in set in an incremental way. And here it's gonna work as before, just allocate the memory and etc. So we can want to see now how that has been working. My bad. Put the point. There we go. It shows you the location that has been all using those operations and the size and etc. Okay, so now we're going to the next step, the memory access. So here we take in both dimensions sum so that we're running the loop. Okay, so here we can see this is just a function, and here is there we go. Here is the most important thing. So here is memory access. Here we create rows and columns, and this is an array of rows and columns. So it's gonna look like as a register, like a register. We can, that's a memory, like a huge register, and now we can target and access any location that memory by using this M. As we can see here, M. We wanna loop through and get every aspect of that memory, right? All of it. Yeah, this is the run. This is give us just the runtime matches with rows, major, etc. Gives rows and columns. So basically, this is how we create, initiate a memory as wanted with number of rows and columns, and this is how we can loop through and target each of them. We can run as well this one. There we go. Now it gives you the runtime of the dimension of the matches with column major order with this such. All right, now we goes the reduce and the integer. So this is gets a little complex in here, but same concept. An example of sharing memory to optimize performance of a parallel reduction by constructing partial result for thread block in shared memory. So here, this is a recursive reduce. This is just a function. We're gonna call it eventually later. But the most important here is the how to complete an arrow for loop and memories. Here we set the thread IDs as usual. We have a boundary check, and here we have in place reduction in global memory, and this is how we place reduction in global memory. We have set up these conditions. We make sure we're not going beyond the boundary set up all the way. And then here we have a rolling wrap. So here we have to not the warp, my bad, a rolling warp, making sure we're not creating any divergence. So we with this condition, we can split the memory going by 32 32 by 1 2 4 8 16 32 as max, splitting it. And here we write a result block to global memory, and here we this is another function to reduce memory. So it's going to work the same way, but this is an important thing, how to set the memory, how to access memory by each thread. And it's going like before, certain boundaries doing the same way, etc. This is that as well, the same concept is going to go the same way, etc. So this is the reduced integer concept of unrolling, and it's whole the same concept, etc. So here, this is different example. Reduce some SMM unroll. So here, we create, of course, we set up this shared memory. We set up a thread ID, global index for blocks for input data process at the time, unroll for blocks, boundary check in here, and then in place reduction in shared memory. But here, because we go with the thread blocks instead of going like in the ropes, we're talking about the block dimensions. So that's why we're using these block dimensions. And here the same, we set up properties and shared memory as before, and we go the same way here like I've seen before. So all these functions work on the same concept of reduce integer, and then eventually we're going to call them here at the end. All right, I can run this code as well. There we go. And we have uh, this every result in that specific kernel. The next is the reduce integer file. So this one is an example of using CUDA shuffle instruction to optimize performance of a parallel reduction. And this is recursive reduce. That's how it works. Recursive reduce sum. It's just a function to we're gonna call later, but the same concept. We set up the shared memory. We set up third ID. We have a boundary check. We convert global data pointer to local pointer for this block. We set SMAM by each thread. This is how we access specific memory, and then eventually we set in place the reduction in shared memory, right within those boundaries, and we unroll the warp, making sure we not get no divergence with a specific every specific aspect of it. And here we have the warp reduce. All right, so we have these built-in functions to reduce every single warp. Then we have reduce shuffle. So this is where the shuffle comes in. And this is by installing this shared memory for each warp sum and boundary check and calculate the lane index and warp index, block warp reduce, and save warp sum to share memory. All right, so that goes the same along as well in here, but yes, the same concept as before. We can run it again. All right, then we have this result as well working here. The next one is a sample shuffle, and here we have this file include sample demonstration of variety of shuffle instructions. So here we have this function we're gonna call. We have the shuffle broadcast, and this is how that works. We're using this built-in function to shuffle. That's the key concept in here. We have this value for specific thread index, and this is where we want to store the output in the specific thread with this specific value after being shuffled. This is a built-in function. This is goes the same way as well in here, and we have a different shuffle up. For example, this built-in function to shuffle up. This one to shuffle down, and this is to shuffle XOR, etc. So these built-in functions help us to do sample shuffle, and we can everywhere. This is the main key in here. We can run it again. There we go. So here it says how we shuffle: initial data, shuffle broadcast, shuffle wrap right, shuffle up, etc., etc. By using these built-in functions. Or now we have a last one. This transpose rectangle. So this transpose rectangle um, is an example of kernel for transposing a rectangle host array using a variety of optimization, including shared memory, enrolling and member padding. So we have here x and y as before and iPad. This is initial data, brain data, check result function. Uh, but the main concept in here is, I think that's, yep. The my concept here, there we go. This is transpose a host. So as you can see here, we have a nested loop, right? And we have an output that store the input, right, in a specific transpose way, right? If you have explaining right. But here we can specify and access each thread in the block dimension and store it. This is what we call transpose host. And now here we have the copy G memory. So we set up those configurations, and then with the transpose with the boundary test, right? We have this condition that this will should not exceed this, and this one should not exceed this, and store it output with the input. This one works the same concept as well. So this is the transpose rectangle concept to check in within this code, and it works all the same pretty much everywhere in here. Now we can run this code in here. There we go. We have for every single function here in the kernel, and it shows the how much you've been taking and with specific grid on blocks. Thank you for watching. That was awesome. Thank you.